In this video, we're going to practice predicting the products of SN2 reactions, and to do this, we're first going to identify the nucleophile and leaving group, and then draw curved arrows for the SN2 elementary step showing how electrons flow, and then and only then drawing the structures of the products. And this is a good problem-solving habit I encourage you to get into. Identifying the key reactive atoms or groups first under the reaction conditions, and then thinking about the mechanism of the reaction, maybe pushing some arrows, drawing the structures of some reactive intermediates on paper if relevant, and then and only then drawing the structures of the products, implied by the mechanism that's most likely to occur after you've thought about the reaction conditions and what's most likely to take place and what's plausible and that kind of thing. So let's start by identifying the nucleophile and leaving group in each reaction here. We'll always be able to find a nucleophile and leaving group if we know the reaction is substitution is SN2, and this is no exception. In each case, the substrate drawn to the left of the arrow here is an alkyl halide, and each of these has a good leaving group linked to a tetrahedral carbon. We've got bromine in the first substrate, iodine in the second, and chlorine in the third. And all three of these are good leaving groups. We're going to end up forming Br-, I-, or Cl- on the product side. When it comes to identifying the nucleophile, one thing you really need to keep in mind is that the nucleophile is often an anion, particularly in SN2 reactions. And in that case, we generally won't write just the anion above the reaction arrow. We'll write an actual stable chemical compound we could use, which is an ionic compound containing a counter-cation with that anion. And usually we can throw the cation away and hardly think about it at all, but you need to do that consciously when you're looking at reaction schemes like this. So for example, NaN3 is really Na plus and N3 minus, a compound known as sodium azide. And the sodium ion, cation, is completely inert. It's the azide anion here that's the active nucleophile. And in particular, it's the anionic nitrogen on the end of azide. Either nitrogen will do, as the anion is symmetric. That is the nucleophilic atom. This is going to donate a pair of electrons to the carbon linked to bromine as the carbon-bromine bond breaks. This is our classic now SN2 type electron flow. And the product here will be an alkyl azide. With this new bond highlighted in red, we can abbreviate this azide fragment as N3. And the butyl group is here intact. And the byproduct here is that Na+, which was a spectator through this entire reaction, and Br-, the conjugate base of the leaving group in the original alkyl halide, right? The last thing I would point out here is the solvent used. And in fact, it's the same solvent in all three cases, DMF or dimethylformamide. This is a polar aprotic solvent that encourages SN2 reactions, encourages them to take place very quickly at a relatively rapid rate. So DMF is a great solvent for SN2 reactions. Notice also that the alkyl halide is fantastic for SN2. It's a primary alkyl halide. The electrophilic carbon is relatively unhindered, relatively open, free, ready to accept the nucleophile quite quickly. And so this SN2 reaction will take place very quickly. And in fact, in the other alkyl halides, we also see primary electrophilic carbons, primary alkyl halides in all three cases here. So the substrates and the solvents are great for SN2 reaction. In the second case here, we again want to separate that sodium cyanide into Na+, which is completely inert, and the cyanide anion, which is the active nucleophile here. Carbon, being less electronegative than nitrogen, is going to be the nucleophilic atom within cyanide. And as we did in the previous case, we're going to use a lone pair at that carbon to form a bond to the electrophilic carbon in the alkyl iodide and break the carbon-iodine bond toward iodine, making I- and this alkyl cyanide, where again the new bond highlighted in red came from this pair of non-bonding electrons in the cyanide anion. And the byproduct here is NaI, sodium iodide, Na+ and I-, where again Na was just a spectator ion through this entire thing. All right. In the third case, we have an interesting alkyl halide. It's worth saying a few words about this benzyl chloride. Benzyl chloride is a fantastic electrophile for both SN2 and SN1 reactions, as we'll see later, as this carbon linked to the phenyl group is quite electrophilic, quite a good electrophile, reacts very rapidly. It's connected to a good leaving group and the phenyl ring, which facilitates substitution at this carbon next door due to resonance and inductive effects, in fact. On the nucleophile side, we've got sodium acetate. And this, again, is just Na plus together with this anion, which is known as a carboxylate anion. This particular carboxylate is known as acetate when we have a methyl group connected to the carbonyl carbon. And the nucleophilic atom in acetate is the anionic oxygen, of course. There are two resonance forms of acetate, and so we could use either oxygen as the nucleophile, I suppose, but why not use the one with negative charge in the structure that we have drawn right here? That sounds good. We're going to use a pair of electrons on that oxygen to create a new bond to the electrophilic carbon, break the carbon-chlorine bond toward chlorine. You're probably sick of hearing me say this by now. And the product now will be a substituted carboxylate, where we have a new carbon-oxygen bond right here made from the non-bonding pair of electrons on the oxygen and acetate in the nucleophile, and to the electrophilic carbon in the benzyl chloride. The byproduct here is Na plus, spectator ion through the whole thing, and Cl minus, the conjugate base of the leaving group. Again, typically you don't need to draw these byproducts when we're predicting the products of organic reactions. The ionic byproducts are taken up in a water layer and pretty much just washed away. But it's good when you're first starting out with a reaction to think about the byproducts, to make sure you understand how the reaction works mechanistically, and for example, what happened to the charges, what's counterbalancing the charge of Cl minus. Or if I know there's negative charge in the acetate and the reactants, where does that negative charge go in the products? That can be easy to miss if you don't think about these byproducts.